Hello everyone. In this video I'm going to help you to get started in solving the problems in section 5.6 about stresses on faults and fractures from 5 to 6. And before we start, I would like to just make here an introductory comment related to faults. In the problems of faults, usually we're going to have three different parts of the problem. The first one is going to be the in situ stress at a particular location. The second one, the fault orientation. And the third one, what are the stresses on those faults? Those three components are somehow independent, and in most problems we know two of these and then we determine the third one. For example, in a problem of ideal orientation of faults, usually what we will know is what is the in situ stress. We know what is the stress on the fault, assuming that this one is going to be at failure. And with these two pieces of information, we obtain what is the ideal orientation of a fault. We know the in situ stress. We assume that the stresses on fault are at failure. And at that point, we get what is the ideal orientation. And all the problems are going to be similar to that. You're going to know two components of this problem, and then you have to determine the third one. For example, when you have to determine what is in situ stress in a particular location by observing the faults, what you know is the orientation of the faults. You are assuming that those are at failure, and with that, you are able to determine the first component, which is the in situ stress. Okay, so let's see how we apply this general procedure and general statement of the problem to problem number 5. In problem number 5, what you know is the state of stress, so that will be component number 1. You know what is the orientation of faults, which are given here from 1 to 4. So you know what is number 2. These two are known. And what we're trying to determine is number 3. What are the stresses on those faults, which may not be a failure, and that's what we actually have to determine. Okay, so let's get started with problem number 5, and we're going to establish here a general procedure to solve this kind of problem, which is a problem of determination of stress on a fault given the in situ stresses, values and orientation, and also given the orientation of the faults. All right, so the first step here is going to be to identify the stress regime. And in this example, I'm going to use the first fault. I'll let you work with the others. And for these particular problems, we have 4 faults, and for all 4 of them, we have the same stress regime. So remember, in this case, we know what the stress regime is, and it's the same for all 4 faults. And if we look at the stress regime, we see that this is SH min 40 MPa, SH max 60, and SV is equal to 45 MPa. So in this case, this is going to be a strike slip stress regime. So I'm going to write this over here. This is going to be strike slip. The second thing that we're going to do is to identify what is the most suitable schematic that we're going to use in order to solve this problem. And that's going to depend on the orientation of the fault and also on the orientation of the stress regime. So in this particular case, we have SH mean acting in direction east-west. And when we talk about fault number 1, we see that this one has a strike which is north-south. And because SH mean is acting in direction east-west, in this case it's going to be easier to make a 3D plot. And that's going to be a little bit more informative than doing a 2D plot. So the second step is going to be to make a schematic of your particular setting that is going to involve the principal stresses and the fault. And this could be either a block diagram in 3 dimensions, or it could be a top view diagram. And in this case, what we're going to do is we're going to use a block diagram because one of the horizontal stresses is aligned with the east-west direction. So let's go ahead and do that. This is going to be the east, the north, and direction down. Let me get a little more space over here. The block diagram, I'm going to draw it as a cube. And in this particular case, we have as information that SH max, SH mean is acting in direction east-west. So this is going to be SH mean. Perpendicular to that, we're going to have SH max. And the third one, SV, is going to be applied on the top face, and this is going to be the intermediate principal stress. Okay, and now we have the schematic of the block diagram with all the stresses. The next thing we're going to do is we're going to place the fault in this schematic diagram. So let's look at the first one. And this is going to be a fault that has a strike north-south, and the dip is 65 degrees towards the east. Okay, strike north-south then means that that's a line that's going to coincide with this axis, and it's going to dip towards the east. So I'm going to draw it over here, the strike on this side of the cube. This is going to be the line of strike, and the dip is going to be 65 degrees. So 65 degrees is going to be more or less a line somewhere over there, where again this line is in direction north-south, and this angle is 65 degrees. Okay. Now, we have the stress cube, and also we have the fault. We have the angles that characterize that fault, strike and dip. The next thing to do is to identify the Mohr circle that is going to allow us to calculate that effective normal stress and shear stress on the plane of the fault. So step number 3 is going to be to identify the Mohr circle. That corresponds to that fault. Okay, so let's see how we identify that Mohr circle. Remember that in order to use the Mohr circle, what we do is we use this particular fault as the combination of the planes that project onto that fault and have a stress which is not zero. And in this particular case, those stresses that project onto this fault, let me draw a little bit more the hidden side of this fault so it's easier to recognize that this is a plane. The stresses that project on this fault are SV and SH min. SH max is if I try to project that on the plane of this fault, is not going to have any component on it. You see, this one is in the same plane of the fault, and therefore is not going to have any effect. The ones that are going to project onto this plane are SV and SH min. And from those two, I have to recognize which one is the largest. And in this case, because we have a strike-slip regime, the higher stress is going to be SV. Let me complete that over here. We knew that from the first step. This is strike-slip. Therefore, SH max is equal or higher than SV, which is equal or higher than SH min. SH min. Okay. So let's go ahead then and draw that Mohr circle that corresponds to this case. The Mohr circle is going to be have a y-axis, which is a shear stress, x-axis, which is effective normal stress, and I'm going to need the effective stresses for SV and SH min. Therefore, in this case, this is going to be sigma v is going to be, I see from the problem, 45 MPa minus 20 MPa. I'm running out of space here. Let me just put the final result. This is going to be 25 MPa, and sigma h min is going to be, where is sigma h min? Is 40 minus 20. That's going to be 20 MPa. I'm going to go ahead and also, although we don't need it for this particular problem, I'm going to compute sigma h max, which is 60 minus 20 and is equal to 40 MPa. Those are the three principal stresses, and those are the ones that are going to be required to use in the Mohr circle. So let me go ahead and draw the Mohr circle that we need, where this is 10, 20, 30, and 40. As we were saying, for this particular fault, we need to use the Mohr circle that involves sigma v and sigma h min. So sigma v is right here. Sigma h min is right here. So the Mohr circle is going to be this tiny one. And in order to see what is the angle that I need to use in the Mohr circle in order to see what is the state of stress at this fault, I have to go from the plane of the maximum stress for this particular circle, which in this case is sigma v. Remember, this dot is sigma v, and this one is sigma h min. Is going to be the angle from the plane of the maximum stress to the plane of the minimum stress. And for this particular case, it happens that that angle is going to be 65 degrees. So when I go to the Mohr circle, what I have to do is I have to go 65 degrees from the center of the circle 65 degrees times 2, that's going to be the angle that I have to use in order to get the value of the normal stress, effective stress, and the shear stress at that particular point, where this is going to be 2 times 65, and this is going to be the radius of the circle. And what is going to be, for this particular case, the center? Well, the center is just going to be sigma v plus sigma h mean divided by 2. The radius is going to be sigma v minus sigma h mean divided by 2. With these two, the center and the radius, I can use these two equations in order to tell me what are sigma n and what are the shear stress with equations that we already know. For sigma n is going to be the center plus the radius. In this case, it's going to be the cosine of 2 times 65. And for tau, it's just going to be the radius times the sine of 2 times 65. So when I apply these equations, I'm going to get what is the state of stress at this point. This point here, that's the state of stress that represents the state of stress on this particular fault, which in this case I have drawn in green. It's just one possible state of stress for the many faults that we have in here. So I'm not going to do the solution for the other 4, but let me just give you a hint for fault number 2. Fault number 2, in the same place, in sedimentary basins, sometimes we have faults in different orientations that may intersect or not, but in this case, the problem says that they are in the same place. This is another fault which strikes east-west with a dip 35 degrees to the north. So if the strike is east-west, then this is going to be somewhere over here, and the dip is 35 degrees to the north. So this is going to be something like this, where this angle is 35 degrees. And it's kind of difficult to see that this is a 3D plane here, but we're just looking in the direction in which it looks like just a line, but this is a plane, okay? This red line is a plane. And if we wanted to solve the stress on that particular plane, we would have to see if we can use this method, the geometrical method. And actually, in this case, we can, because in this case, SH mean, it's in the same plane of the fault. So that means that we can use it because the stress is just going to depend on SV and SH max. And the stresses on the Mohr circle that I need to solve this particular problem is the stress sigma H max and sigma V, which in the 3D Mohr circle, sigma H max is going to be at 40 MPa, which is going to be here. And in this case, this is a combination with sigma V. So the Mohr circle I want in this case is going to have another center, another radius, but it's going to be this circle. And the angle that I need to use now is going to be, remember, the angle from the plane of the maximum stress, which is sigma H max, to the plane of the minimum stress, in this case, in this Mohr circle, which is sigma V. So I'm not going to tell you what that angle is, but I'm going to tell you it's not 35. Okay? It's not 35. And when you solve the problem, your state of stress for that particular place with a new center, this is the red, and with a new radius, is going to be somewhere over here. This is going to give me now the effective normal stress and the shear stress for that point. And as you may expect, if you have another fault which is oriented in a way that it includes the direction of SV, then you're going to need to use a Mohr circle, which is a combination of sigma H max and sigma H min. And you will have to find the angle that is needed in order to represent that in the 3D Mohr circle. From all these four cases that I have, there is one of those that cannot be solved with this geometrical method because it's not going to be aligned with any of the principal stresses. In that case, you just tell me that you cannot solve it with this method. And if you wanted to solve it, what you have to do is to use the tensorial method. And that's the next problem. That's problem number 6, which I'm not going to ask you in this case to solve on your own. If you want to do it, I can help you with, but I'm not asking you to do it for this particular homework. This is optional. And if you wanted to solve that, what I recommend is that you check GitHub code from Daniel Barrera. Let's see, let's look at his ID. Where is that? I think this is mine, yeah. Oh, here it is. So if you look at his code, then you're going to be able to download that and to play with that code and have a solution which is similar to the one that I showed last time, which is this one over here, in which by using the tensor method, we can tell what the state of stress and what the normal stress is for a given fault. If you want to know a little bit more about that, also check my YouTube videos in advanced geomechanics. In that one, I give a little bit more of an explanation about the tensor method used to compute normal stress and shear stress for a plane in an arbitrary direction in 3 dimensions. But in this case, we're not going to do this one. So, or it's not mandatory, so don't worry. All right, so let's talk about problem number 7 then. Problem number 7, it's a problem that involves determining what is the maximum stress possible at a given site, assuming that I'm at the limit of frictional strength of the faults. And if we come back to the diagram that I showed before, in this case what we're doing is we are assuming that we are at the critical orientation of a fault, and we're also assuming that that fault is a failure. So by assuming these two, what I want to do is I want to calculate what is a possible state of stress, or what are the limits of state of stress that are compatible with this condition of stress on the fault at failure. So this is going to be, we know 2 and 3, we're going to determine 1. So let me just write that down. This is a case that we know 2, we know 3, and we are going to determine 1. In this particular case, you just have to determine the magnitude of the stress. I'm not asking you for the orientation, but there might be some other problems where you also need to determine what is the orientation of such stress. Okay, so let's see how we solve this problem. Um, Here we're going to have two cases. One is going to be normal faulting, and another one is going to be reverse faulting. And for those two, in the range from 0 to 5 kilometers and assuming hydrostatic pore pressure, I like that you tell me what is the minimum possible stress for normal faulting or the maximum horizontal stress for reverse faulting for two friction angles. So let me just do a schematic of what the solution is going to look like. If this is depth, and if this one is the vertical stress, and this one is the pore pressure, the minimum possible horizontal stress is going to depend on the friction angle. The lower the friction angle, the higher that minimum principal stress is going to be. The bigger the friction angle, the more capacity the rock is going to have to bear that stress anisotropy. So after you put all your numbers, remember the first thing that you have to do is to compute the vertical stress. This is what you know in this case. So you know SV, you know pore pressure, then from here you get what is sigma V. Once you know sigma V, and either if sigma V is the maximum effective principal stress, then from here you can calculate sigma 3 by doing sigma 1 divided by Q, or if sigma V, as in the second case, is going to be sigma 3, then you can calculate sigma 1 as sigma 3 times Q, and from these two, adding pore pressure, you can get either the maximum, the least total principal stress, or the maximum principal stress, which in this case, this one is going to be for normal faulting, is going to be SH mean, or this one is going to be SH max. So after you do all this workflow, depending on the friction angle, you're going to get a solution which is somewhere over here. And where it exactly plots is going to depend on the friction angle. As I was saying before, the higher the friction angle, the higher is going to be the anisotropy ratio that the rock can support. Where this is going to be for a particular depth, this is going to be, let me zoom in there, this is going to be sigma 3, and from here to there, this is going to be sigma 1. So the higher the friction coefficient, the higher the anisotropy, or the difference between those two, and the smaller sigma 3 is going to be, and therefore the smaller sigma h mean. And again, you're going to do two cases, and those two cases I'm going to make this line to vary as a function of the friction angle. And what this problem is trying to illustrate is what is the effect of that friction coefficient on the minimum possible horizontal stress. For the second case, is going to be similar. Again, we're going to have here SV, something that you know. You're going to have hydrostatic pore pressure, as we have assumed in this problem. What you have to tell me now in this case is what is going to be the maximum value of SH max. Let me try to draw the line again. What is going to be SH max, also depending on the friction angle. The bigger the friction angle, the higher SH max is going to be. And let me just complete this for a particular depth. This is going to be sigma 3, and this is going to be sigma 1. Okay, so I think I have given you enough hints in order to solve problem number 7. Problem number 8, it's very similar to problem number 7, this part, because it's a normal faulting, but in problem number 8, you need to consider what is the effect of water. So remember, whenever you have water, then you need to consider the depth of the seafloor. That's going to affect what is your vertical stress calculation, and therefore is going to affect the final results as well. And the interpretation of this problem number 8 would be something like this. You have 500 feet of water depth, and you need to calculate what is the stress at depth. Let me read this problem. At okay, so it's at 2,000 feet of depth, and what you know is that in this case, you know also what is the overpressure, and you need to determine the horizontal stress. All right, so let's add here 1,500 feet in order to consider what is below the seafloor. And what is happening at this particular place is the assumption is that you have faults that are going to be limiting what is the state of stress in this particular location. So, for example, if you were to have a sandy reservoir, let's say somewhere over here, that means that if you have a fault, a normal fault, then this one is going to be this particular sand, maybe may continue somewhere over there, or if it is here, it might be somewhere over there. Remember that always on the hanging wall, the position is lower relatively to the same position on the footwall. And what you're going to have to do is to use the same procedure that we have been using all the time. First, you calculate total vertical stress. Second, you calculate pore pressure. From those two, you calculate the effective vertical stress. Once you know the effective vertical stress, what you're going to do in this case is, instead of using the equations of elasticity as we did before, what you're going to have to use is this new equation that relates sigma 1 and sigma 3. I'm not going to tell in this case which one is sigma 1 and which one is sigma 3, but I hope that that you recognize that quite easily, where Q is going to depend on the friction angle, as you know. And after you compute the value, in this case, of sigma H mean, and since you know the pore pressure, you're going to be able to calculate what is the total horizontal stress, the minimum total horizontal stress at this depth. And in addition, I'm asking also to draw the Mohr circles and to repeat this calculation for the case in which you have hydrostatic pore pressure. So for this case, I'm going to ask you two solutions. One is the one with lambda p equal to 0.78, and another solution considering that this is hydrostatic. Okay, so these are going to be two solutions. I just want you to capture and to see what is the effect of having a much lower pore pressure and how that's going to affect the size of the Mohr circle in this particular case. Okay, just one more thing I'd like to say about problem number 8. And this is something that, remember, the workflow, I want to insist on this because it's very important, but we have already seen it. And when we calculated the stresses before, we already used this, but when we get to the step of calculating effective stresses, we use the elastic equations, right? Which is step number 4. Okay, so you see the workflow is exactly the same all the time. SV, pore pressure, effective vertical stress, then you calculate horizontal stress. Before we use this theory of linear elasticity, but now we are in this point. Instead of using that theory, we're assuming this is already a failure, so we're using now the equations of stresses on faults, and that equation is this one. And after you finish 4, then it comes back to the same procedure that you have already seen before. So this is a problem that you have already seen that we're going to use a lot in this class to determination of horizontal stresses, either through the elastic method or through the failure method. But remember, the procedure is always the same. And with that, let's just finish with problem number 9. In problem number 9, I like this problem a lot. What you have to do is to look at this map from the Eagle 4 formation and try to interpret that map to look at the faults and see how you can interpret what is the state of stress. And also, in this case, we're not particularly interested in what is the magnitude of the stress. We want to know more about the orientation. All right, so let me enlarge the window over here. This is the map. In this map of the south of Texas, here we have the Eagle 4 formation, and what you see in the blue lines is the strike line of the faults. And what this is telling you is that all these faults that are mapped on South Texas are in direction of more or less, well, I'm not going to tell you a number, I like that you solved that, but you can see it's more or less going in the northeast direction, so tending in this angle, northeast to southwest. And what I like that you recognize from here is assuming or knowing that we are in the case of normal faulting and we know what is the strike of these faults, I'd like that you tell me what is the orientation of the minimum principal stress. Let me make a small drawing of this. On the right, these faults, which are in blue, I'm going to simplify here on the right. Remember, all of these lines are telling you what the strike angle is, where this is the north. So this is going to be the strike. We cannot see the dip over here. So the dip we cannot see, but it could be either in this direction or in that direction. We do know what is the strike. So if this is normal faulting and you know the strike of those faults, you should be able to tell me what is the direction or the orientation of the principal stress in this case. Again, I'm not asking you for a magnitude of that stress. I'm just asking you about the orientation. And after you figure that orientation, I like that you check that and you double check that with another piece of data in order to verify that your answer is correct. And that's going to be the orientation of horizontal wellbores in the Eagle Ford basin. So if, again, if this is the strike of your fault, you should be able to tell me what is the direction of the horizontal stresses. And once you verify that, I like that you check that with the orientation of horizontal wellbores in this particular place. And in order to do that, what you're going to do is to use this tool from the Railroad Commission that allows you to see the surveys of wellbores and also of horizontal wellbores. So if you go ahead and you click in here, you're going to get to a map like this one, in which if you zoom in next to the Eagle Ford, at some point you're going to start seeing the line of the counties. And if you zoom a little bit more in a particular place, I'm concentrating here in the Frio County, you're going to start to see the wellbores, the leases, and also their orientation. So there you see the wellbore showed up, and the lines here are telling you what is the predominant direction of horizontal wellbores in this location. If you remember what we have seen from hydraulic fracturing, we want these horizontal wellbores ideally to be in the direction of the minimum principal stress in a place subjected to either normal faulting or strike slip. So you could see that there are some other wellbores like this one or like that one or those ones that are not exactly oriented in this direction of which is a predominant, and that may be for some other reasons, probably some surface constraints. But if you zoom in, let me come back over here. If you zoom in enough, you will see that the predominant direction in this location is related to the direction of your faults. So that's your job, and that's what you have to do. You have to reconcile and use these two pieces of data in order to explain what is the direction of faults at this particular place in the south of Texas. So one more thing that which I think is fun just to mention, we know that the Eagle Ford is over here, and I don't know if you have seen the satellite image, but these are very nice. These show how south of Texas looks at night, and you can see, for example, this is Austin, this is San Antonio, Corpus Christi, Laredo, And what you have here are not big cities, are not big neighborhoods. These are the lights from drilling activity in the Eagle Ford, and you see how it light up nicely coincides with what we have in our map. All right, okay, that's everything for this video.